I'll hopefully see my screen. Great. Okay, so hi everyone, I'm Matthew. I'm a postdoc here at Oslo, and I'm going to be giving an update on BeyondPlanck, which is the first of the CosmoGlobe projects where we worked on Planck LFI. So as most people know, Planck is of course one of our best sources of information about the early universe and the CMB itself. It has basically some of the best constraints on almost all of the cosmological parameters that we have in the Lambda CDM model, as well as various extensions of that model. And so Planck is, with no understatement, probably our most valuable resource about the early universe that we have at the moment. But that's not to say that the Planck data is in itself perfect. If you look at the Planck 2018 data release, which was the final at the time that this project started was the final data release for the official Planck collaboration, and you compare it with the WMAP data that had been taken by the WMAP satellite. In theory, these two things were supposed to see exactly the same skies. But in practice, when you take these difference maps, what you saw was sort of large-scale polarized systematics that you can see here, which indicated that there were still some outstanding problems either in Planck or in WMAP or in both projects. And these were the sort of things that we were interested in resolving through some sort of joint analysis between both Planck and WMAP. Additionally, we knew that we had outstanding problems with the Planck data itself. So this plot shows the gain solution as a function of time over the whole mission for one channel on Planck LFI. And you can see the black curve is the Planck 2015 gain solution. And then the blue to red curves are the 4 iterations of the gain solution that were able to be run before the 2018 data release. And so you can see that as you iterate on this pipeline, you get the gain solution is clearly changing and looks to be converging towards some sort of new solution, but that the convergence has not been achieved in these 4 gain iterations that were able to be run in the time and manpower that the official Planck collaboration had. So another question that we set out to answer with BeyondPlanck is what would happen if we could actually finish this iteration process and explore the full iteration of all of the various parameters, not just the gain, and what sort of results would we end up with then? And additionally, as I sort of mentioned before, we know that in polarization in particular, that both Planck and WMAP had large scale that were known to not be very well measured. So here you can see the Planck 2018 gain residual templates. So these were basically fitted post hoc to the maps, and these are basically modes that Planck knew that it had not done a very good job of measuring, just purely because of the scan strategy and geometry and things like that. By comparison, we could see basically the exact same sort of a thing in WMAP. So this is the WMAP K-band imbalance, or transmission imbalance template. And these were the modes that WMAP knew that it wasn't really able to measure very well just because of its scan strategy. And so if we look at these difference maps that I showed before, you can see that basically these large-scale polarized differences look, not 100%, but look to be at least strongly correlated with these known modes that the 2 experiments knew they hadn't done a very good job of measuring. And so another question that we were trying to answer with BeyondPlanck was, could we use these 2 experiments to constrain one another? So because these two sets of poorly measured modes do not look alike, we were hoping that we could use Planck to constrain the poorly measured modes in WMAP, and vice versa, use WMAP to constrain these poorly measured modes in Planck, and then be able to use that to really hammer down these large-scale polarized systematics. So that's where we started. We wanted to try and speed up this iteration process to be able to perform hundreds of component separation and calibration iterations instead of just the 4 that they were able to do in 2018 by emailing data products to one another. And number 2, we wanted to break these Planck-specific degeneracies by using external data, in particular WMAP. We chose the name BeyondPlanck to recognize that this work, of course, builds on and is a natural continuation of the official Planck analysis effort. So although we did develop some new algorithms, the vast majority of the code that we're using is based strongly on the existing Planck data analysis effort. And also, but we've added beyond to emphasize that it involves not only Planck, but also many other data sets. So one of the reasons that we used iteration as such a that it's such a powerful tool in this case is this so-called chicken and egg problem that we see in the CMB field. So especially on full sky satellite experiments, the data is basically this sky signal, so the various sky components, so the dipole and the foregrounds and the CMB, convolved with your instrument calibration. And so that's basically at the very simplest form. That's how the data looks. But unfortunately, to know this instrument, to sky signal, you of course then need to know the instrument calibration, because without knowing your gains and all of those parameters, you can't tell what amplitude and what additional noise you have in your maps of the sky. But of course, the best way that we have, especially for these full sky experiments, to calibrate your instrument is to compare them to the maps of the sky. So you look at the signal that you expect, and then you look at the signal that you have, and you basically calculate a calibration signal there. And so obviously you can see where this degeneracy comes in, where we need to know one of these things to determine the other, and vice versa. And so this is a reason that iteration became a natural solution to this problem. So you can iteratively estimate the sky signal and the instrument calibration one after another, and have them both converge simultaneously to the maximum likelihood solution. So as Ingen mentioned in her talk, the way we do this is an end-to-end iterative analysis. So traditionally, you would have done each of these steps once, or in the case of Planck 2018, 4 times, and then you would end up with final results and publish those. But in our case, we have built this entire iterative loop where all of the results of the various steps are fed back and fed forward into all of the other various steps in the loop. And if you run this a large number of times, you end up exploring the full posterior distribution of all of these parameters. And so that's sort of where the idea behind the BeyondPlanck pipeline. So our main goals were to implement this end-to-end analysis framework for current and future CMB experiments, using our experience from the actual Planck DPC analysis. We wanted to demonstrate this framework on Planck LFI data. And the reason we selected LFI as a starting point is because the LFI data set is both easier to work with, has fewer systematic properties than HFI, but also it's smaller in volume, and that makes it easier to run on our computing hardware. And then finally, we wanted to take this software and make the results publicly available under an open source license, and provide them to the wider community. And that's sort of what this continuation, the Cosmoglobe project, is all about. Is taking this pipeline and generalizing it to be able to use as much data as people have available, and have it be useful for other people's projects. So this is the BeyondPlanck collaboration. So we have a large number of people here in Oslo, but we have many other collaborators at various institutions in Europe, and then some external collaborators in the US. And so this is the group of people whose work I am presenting today. So here's our pipeline in a single slide. So BeyondPlanck takes a Bayesian approach to this whole process. And so the first step of a Bayesian approach is, of course, to write down a parametric model for your data, which you can see here. And we'll go in a minute into detail about what all of these parameters mean. But in general, then what you do is you take omega, which you let be the set of all 3 parameters. You derive the joint posterior distribution using Bayes' theorem. And then you just map this joint posterior distribution out with standard MCMC methodology. So in general, this sounds very simple. The difficulty is, of course, that the size of this posterior distribution is massive, and that makes it very difficult to get out. And so we'll discuss in a minute why or how we managed to do that. So here's the data model again. We see on the left-hand side of the equation, this is our data as a function of time that comes out of so these are the raw time streams that come out of the telescope. We have the sky model here, which we'll discuss in detail in a moment. There's a main beam term, a pointing term, a gain term, a bandpass shift term, side lobe pickup, the orbital dipole, correlated noise, and white noise. So these are the various terms that went into our sky model for LFI, and of course for other experiments, it is easy to generalize and extend this data model to add additional terms if they're required. So for the sky model, these were the various components that we used in our analysis of LFI. We had a CMB term, synchrotron, free, AME or spinning dust, thermal dust, and point sources. But again, this is not an exhaustive list of all of the sky components that you could use. And so we have or are currently in the process of developing modules for various other components like zodiacal light that you'll hear about later. So then, as I said, what you do is you take omega, let it be this set of all of these parameters, these millions or billions of free parameters in your model, and you map it out. And the way we do that is with this process called Gibbs sampling, which is basically an MCMC method that allows you to look at these huge distributions in an iterative way instead of trying to directly invert the whole thing. So as I said, what we're trying to do is this full iterative pipeline. And what we do is we, using Gibbs sampling, map out each of the independent variables in succession, holding all of the other ones fixed. So we map first the gain by holding all of the other, all variables fixed, and then the correlated noise holding the gain and everything else fixed, and so on and so forth. So this is just a graphical representation of what Gibbs sampling looks like in 2 dimensions. So if we have some initial point that's shown in black here, and we have this probability distribution that is these curves. So in Gibbs sampling, first, we would hold one variable fixed and select a new point along the axis of the other variable, and then we would then hold that variable fixed and select a new point, and so on and so forth. And as you follow this procedure, eventually you end up mapping out the whole probability distribution without having to, while only having to draw samples from one dimension. So that greatly simplifies this process and allows us to basically do this at all. Because if you had to directly sample from this full million or billion dimensional probability distribution, that would be impossible. So a few words about the data that went into the BeyondPlanck pipeline. So because this was a sort of a pathfinder project, and we knew that we were going to have a lot of difficulty getting this to work algorithmically, we wanted to make this easier on ourselves. And make sure that we could show that when we had developed these algorithms that they were working properly. We wanted to make sure that the actual data that was going in the time domain was the dominant source of information about the sky. So for that reason, we have the Planck LFI time ordered data, and then we have some other things at the map domain that were designed to constrain the sky model at the same time. So we had Planck 857 that would constrain thermal dust intensity, Planck 353 in polarization only to constrain thermal dust polarization. And then we had the WMAP 33 to 61 gigahertz in T and P to help with low frequency foregrounds. And then we had HASLAM to constrain the synchrotron intensity. But what this means that we did not include is the intermediate Planck and WMAP data, because those have higher signal to noise ratios than Planck LFI, and they would, if we included those, tend to dominate our CMB maps, despite the fact that we are not correcting them for all of these effects that we're modeling in Planck. So for those of you who were here a year ago, I'll just give you a short reminder of where we were at that point. So we had basically a full functioning pipeline. However, there were some outstanding issues that we were still in the process of tracking down. So we had residual striping in the southern hemisphere. And so that meant that we only were calculating our cosmological results over the 36% of the sky in the northern hemisphere. And you can see if we included the full sky map, that our chi-squareds were very, very bad. And so that meant that basically we were throwing away half of our data at the end of the day, which was obviously not ideal. We were still for the very low level processing, so the ADC corrections and other low level data features, we were still using the DPC pre-processed data for that. So this was the thing that had been created in 2018, and we were not changing that at all or iterating on any of those estimates. So that was one thing that we have updated since then. And additionally, we discarded about 17% of the 44 gigahertz data because of how the 1/f noise model appeared to break down for some of the channels for about half of the flight. And so you can see the effects of that here, where we ended up at 44 gigahertz with higher noise than either the 2018 analysis or NPipe. And finally, a minor thing, we were still using noisy bandpass measurements, which is another issue that has been fixed for this data release. So since then, we spent a bunch of time trying to correct all of these effects, both major and minor, and we think that we have basically tracked all of them down, and we have the data in a state that we are happy with. So the first of these major effects that had probably the largest impact was the gain smoothing. So the gains are estimated per time chunk, but of course this estimate is very noisy compared to what we would expect from a physical instrument. And so to get a less noisy measurement, what we do is we smooth the gains over a chunk of pointing periods to get a smoother looking curve. And originally what we were using is basically a boxcar filter over these gains with some special exceptions for gappy periods or places where we knew there were big jumps. And when you do the boxcar gain smoothing, you end up with these sort of large scale stripes that we were trying to track down. However, we've since switched to a Wiener filtering gain system, which allows us to basically get sort of the optimal estimate for this smooth gain from the noisy data. And when you do that, it seems to eliminate these large scale stripes that we were seeing in our maps. So that's been great. And on the right here, you can see a comparison of our new gain estimate with the DPC and NPipe. And you can see that we largely agree quite well. There are some minor deviations in various locations. So, and then another thing that we've done is improved on our noise modeling. So it turns out that the problem with the 44 gigahertz data that we're seeing, that it was not well fit by a standard 1/f noise model. And indeed, it appears to have some extra contribution from a second component. So we added a log normal component to our noise model for some of the channels, and this allows us to much better model the resulting noise in the time streams using this method. And so the other feature is that we are fitting these noise time streams as a function of PID. So one fit per time chunk, whereas the DPC was fitting them as a single value per the whole flight. And so we believe that our methodology is an improvement over that, and you can see evidence for that on the right here. So this is one of the noise parameters, alpha, as a function of the whole flight, and on the top here, this is a thermometer temperature that is close to the relevant detector here, and you can see that this noise noise parameter matches very well with the features in this thermometer time stream, and so we believe this is evidence that what we are mapping here in a per PID basis is basically a good representation of a physical change that's actually happening in the system. And so this we feel like is good motivation for modeling this in this way. I also mentioned that we were previously using noisy bandpass measurements. So you can see here that the original bandpass curves that were used in the Planck DPC analysis are these orange curves. which have sort of noisy features at one end and this sort of weird overhanging bit on the left end of some of the bandpasses. And so we have, and those were known to be errors from the measurement, not physical effects of the bandpass. And so we are now using these new corrected bandpass curves that we believe are superior in every way to the previous ones. So this is a minor change, but it did have a small impact on our bandpass shift calculations. So you can see the overall bandpass adjustments that we apply to each channel here. And in general, they are quite small, but they do have a significant impact on the resulting maps. And then finally, another minor thing that we've corrected for is we've now implemented and are using our own ADC corrections. So correcting for the hardware problems with the analog to digital converters. And so you can see on the left here, this is the binned RMS of the ADCs as a function of voltage. And that these dip features here are what are known to be these ADC nonlinearities that were the issue. But there also is this sort of hash of what we think is noise on top of that. So the previous attempts or the previous algorithms to do this basically steamrollered this entire curve to be flat and gave you a correction that looked like this red curve down here. And what we've done is instead said that perhaps this blue stuff, this hash is probably not worth correcting for and is some sort of physical effect or is just noise. And so we are just fitting these dips out of the ADC correction and using a much less aggressive correction for this ADC term. So that's been our effect of the ADC corrections. It doesn't appear to be a large effect in the resulting maps, but we do believe that it is a superior way to handle this problem. So now we'll talk a bit about the products that we've created. So traditionally, most people are familiar with CMB experiments releasing just a set of maps or something like that. But in our case, what we have is in fact an ensemble of the full samples of all of these parameters over time. So you can see here that as a function of iteration on the bottom, these are various time domain parameters like the chi-squared of a particular channel, the gain of some channels as a function of iteration. And you can see basically that we have the full result of exploring this whole posterior distribution over all of the iterations that we have computed. And we have also, in addition to sort of one-dimensional parameters, we also have map domain parameters in the same way. So these here are just some GIFs of looking at the correlated noise in 4 different samples. See the CMB in Stokes Q, the synchrotron polarization in beta, the synchrotron in Stokes, the CMB in Stokes Q and the synchrotron in Stokes Q. And so we have all of these parameters basically for every single parameter that we estimate, we have on disk as a set of what we call the chains file, which is basically the full set of all the samples that have been computed by our pipeline. So one thing, this is obviously a very powerful method that allows us to do stuff that possibly or that otherwise couldn't be done. So one thing that we've gotten out is noise correlations. So you can look here. These are our noise parameters for each of the channels. So we've got 4 parameters at 30 and 44 gigahertz because we added this extra log normal term, and then 3 parameters at 70 gigahertz where the log normal term wasn't required. And you can see that as you can see that basically this is a huge correlation matrix of all of these parameters correlated with one another. And basically the structures in this map are not well understood yet, but this is sort of, you get this for free basically using our sample set approach. And there are many other parameters that you can compute these sort of correlations between and there's all sorts of interesting stuff that you can do with that. But yeah, so we have an ensemble of all of these frequency maps, and so this is This is the CMB at Stokes Q, and so you can see for each sample number, we have different realizations of what the CMB looks like as the other parameters in the chain take very slightly different values. And so all of these are statistically consistent estimates of CMB at 30 gigahertz. Not of the CMB, of the map at 30 gigahertz. And they allow you to basically do statistics on this map and get data-driven errors in that way. But in addition to, of course, you can also compute the posterior mean of all of these samples, and that's what's plotted here. So these are sort of our best estimates of the mean of our posterior distribution. So these are the things that you could compare to sort of a traditional CMB analysis pipeline with these mean maps. But in addition, we also have the full correlated sample set of all of the realizations of each of these maps. So that allows you to compute the errors on them directly from the data. So a few words about the computational resources required to run this pipeline. So we have compressed the data on disk to about 1.5 terabytes of data, which sounds like a lot, but we are able to buy computing nodes off the shelf that have 2 terabytes of RAM now. So it is possible to run all of this pipeline on a single node, we can do one single Gibbs iteration, so one estimate of every one of the parameters in about 164 core hours. So this node has 128 cores, so you divide by 128, and it's like about 1.3 hours per 1.3 like wall hours for a single one of these samples. So that means that we can get the full chain was, or the full sample set. We generated 4 independent chains of 1,000 samples each on 2 different nodes, and the total wall time was about 15 weeks. So although that does sound like quite a bit, it's still doable in finite time, and does allow you to get this full sample set. The total CPU cost was about 600,000 CPU hours, which, when you compare with the Planck DPC analysis, for instance, the one single realization of the full focal plane simulation set for Planck costs about 10 to the 4 CPU hours, and so that was not counting any of the actual analysis. That was just the simulations. So we have basically sort of even less runtime, even though we are still computing this full sample set. So we can look at the comparisons between our maps and the other maps that have been produced with the same data set. So at the top here, this is the LFI DPC gain template that we saw earlier. So these are the poorly measured modes that LFI knew that they wouldn't do a very good job of measuring. And this is our at 30 gigahertz in Q and U. This is us minus DX12, so the 2018 data release, and the same thing here for NPipe. And so you can see that clearly these difference maps trace these poorly measured modes pretty well, and that to us implies that we have managed to correct these modes through the addition of WMAP. Which was our original goal, was to stabilize these modes using other large-scale estimates of CMB polarization. And then if we compare to WMAP, we can see that these are difference maps with WMAP 30 gigahertz. So this is Planck 2018, this is NPipe, and this is us. And you can see that we have lower amplitude residuals with WMAP. And that the residuals that we do end up with look a lot like this WMAP gain imbalance template, which is our large scale modes that WMAP knows that it has not done a very good job of measuring. And so the correcting for these modes in the WMAP data using the Planck data is a project that's ongoing that you'll hear about later. So these are our power spectra of our frequency maps. So you can see that we have very flat noise because we are modeling and correcting for our noise. and we're using basically, because we have a sky model that is joint between all three of our channels, it allows us to use information from various frequencies to correct for noise in other frequencies. And so that allows us, that's a very powerful tool that helps with noise estimation. NPipe still has lower noise at high frequencies in most channels. And that is because they do an extra algorithmic step of smoothing the reference load, which is the final thing that we have not been able to do yet. And I'll talk a little bit about that later. But yeah, so our spectra are flatter than NPipe, however. So you can see NPipe has a slight slope, and we think that that's because we have less correlated noise in our maps because of this joint multi-frequency signal estimation. But we have higher white noise, as I mentioned. So this is what our astrophysical foregrounds look like in temperature. So we have synchrotron, free, dust, and AME. And these again are the posterior mean maps. And this is what synchrotron looks like in polarization. So this is Q and U. And then this is the beta maps and the arrow. So this is what we get for our polarized foregrounds. Additionally, we have put some constraints on polarized AME that we basically have managed to do a full sky constraint on AME polarization. And you can see that we have that constraint, the maximum AME polarization as a function of a prior on the synchrotron beta. And so these are highly degenerate, but we are yeah, for realistic values of beta synchrotron, the limit is sort of less than 1 or 2%. So yeah, and then this is what our CMB temperature samples look like. So you can see that we've managed to get rid of the large scale polarized. Well, actually, you can't see in this plot, but yes. So this is what our CMB temperature samples look like. This is what the power spectra of our CMB maps look like. So this is in TT, and you can see that these are the deviations from the model plotted. So we are in black, and then you can compare with WMAP and Planck, and that we largely agree with the deviations that have been seen before. And then this is our low L TT spectra. So you can see that we have asymmetric error bars here in black, and that again we largely agree with Planck 2018 in most cases. So we also have the CMB solar dipole estimates, and once we have run this full pipeline, we end up with a CMB solar dipole estimate that, in amplitude at least, that is very close to what Planck HFI found in 2018, and so that's great that everything is consistent there. Then we have cosmological parameter estimates. So you can see here these are our 6 standard cosmological parameters, and we have these banana plots. We also have an estimate of R, although of course this is not the data set that you would want to estimate R. So we have less than 0.8, which I'm sure everyone's really excited to hear. And then this is our tau estimate. So tau basically is one of the things that's most sensitive to low L polarization, which is where we think that we have our biggest improvement in this pipeline. So here this black curve is still a preliminary tau, but we don't expect it to change very much. So this is our estimate, and then you can compare it with various other literature estimates here. So this yellow one is WMAP. And this blue curve is what has been previously found with LFI and WMAP combined. So we're actually closer to the HFI measurements than previously found when we do our full analysis. So this is just a plot of convergence of tau. So because tau is basically the most sensitive thing to low L polarization, we looked at tau as a function of iteration, sort of as a proxy for whether or not we had fully explored our distribution. And you can see that after about 2,000 or 2,500 samples that we had sort of converged on a value of tau. And so this led us to believe that we had enough samples that we had fully explored our full posterior distribution. So naturally, Hans Christian was very excited about that. And he held a press conference, which looked somewhat like this. Yeah. So basically, we all of this has been performed with Commander 3, which was a direct generalization of Commander 2, which most people are probably familiar with. Basically, Commander 3 is going to be the central pipeline of Cosmoglobe going forward. So for those who are interested in getting involved with Cosmoglobe, I would direct you to the Commander 3 GitHub, where you can look at all of the code. Everything is available under an open source license. You can also find our BeyondPlanck products on our BeyondPlanck website. Yeah, so right. So this is sort of the state of things from BeyondPlanck. And of course, I'm sort of teeing off the rest of this week's discussion by saying this is where we would like to end up, right? Is with sort of this fully integrated model that includes all of the data that we now have available and in this full Cosmoglobe sky model and pipeline. So to summarize, we've managed to successfully implement this framework using Planck LFI. The framework has a lot of different important advantages. So we can do joint instrumented foreground modeling, we can do end-to-end error propagation, we can use physically motivated models for our sky parameters and for our instrument parameters. We can do multi-experiment analysis in the same pipeline. We have many different multi-level goodness of fit tests. We don't require intermediate human interaction, so there's no emailing of data sets to one another. And we have high computational efficiency, which allows us to do complicated data sets in a reasonable amount of time. And of course, the next steps are to generalize and populate this framework with as many data sets as we can get. So again, yeah, everyone is welcome to get involved and add data or work on other people's data using this open science Cosmoglobe community. So just to sum up LFI, because hopefully this is probably the last time we'll talk about LFI at one of these Cosmoglobe meetings, because it's now basically finished. So we're going to have our cosmological parameters estimates out soon. There's only a couple things that are left to be cleaned up. The first one is to finish writing these papers. You can see on the right that we have 5 of them are currently available on ANA, and many others are in the submission pipeline. And then the final thing, as I mentioned, is the reference loads filtering that NPipe did. And we know that will improve our final product by reducing the white noise level. But computationally, it requires a complete rewrite of all of our noise modeling code. And so we are going to wait until we can get to that before trying to add this reference load filtering to LFI. But yeah, so in general, LFI is a data set that's completely ready to be used in joint analysis with whatever data sets that other people are interested in using it for. So, and then just as a preview, here we have the next steps. So this is what I'm working on right now is starting on HFI analysis, and so you can see that. Because this plot is in microkelvin, that we've already recovered about 10 to the 14 more signal than the HFI DPC analysis did. So we're just waiting on Stockholm to give us our Nobel Prizes for this one. But in general, yeah. So we have the data and we're able to read it in and make maps from it, even though the maps end up looking like this. So we're working on that, and we're hoping to have some progress on that this year. So yeah, this is the obligatory thank you for the funding slide. So thank you for the funding, and thanks everyone for listening. I'm happy to take any questions.